think some of you here do similar, have a similar approach to doing research. The main difference maybe is that I usually work on abstract data. Many of you work on more concrete data, 2D, 3D data. But of course, there is lots of overlap in between. And just the promised 2 slides about the index structure type work I did, the X tree. Back then, we looked into the reasons why some of the nearest neighbor queries didn't work well in high-dimensional spaces. And we found out that the R tree index structure generates a high degree of overlap. If you know the R tree, which is a rectangular tree type of thing, basic index structure, and my boss at that time, my PhD advisor, Hans-Peter Kriegel, he was one of the inventor of the R star tree, which is like the commercial variant of the R tree. And we found out there's lots of overlap in the directory, and you see that here. And the idea was, why don't we try to avoid the overlap in the cases where we can avoid it? And the idea was basically then generating types of supernodes in between, and this dynamically depending on the dimensionality and the properties of the data. And the supernodes that you see here are just generated if it on average, and there is a formula for calculating that, if on average you have to access both sides anyway. If there is too high, if there would be too high degree of overlap in the directory, then you don't split them. Why should you split them if you have to access them both anyway, right? So it's faster to have them consecutive on storage instead of kind of having 2 page accesses. So this turned out to be better, and there's another theoretical part of it. You can theoretically define an overlap-free split, and in cases that is possible, you use, of course, the overlap-free split. And both is like mathematically founded and works well. And basically what you get is